Hello, my name is Karim Aboudaoud. I'm a data scientist at Robin. So given that you guys have watched the previous videos, this is just a continuation of the optimization algorithms that you can think of when visiting the hackathon problem. So in this video, we're going to focus on three main pillars, which are going to be heuristics and meta-heuristics, machine learning, and reinforcement learning. So to start off, heuristics and meta-heuristics, we're going to talk about exact versus non-exact strategies, heuristic algorithms, and an example of heuristic algorithms which are nearest neighbor, meta-heuristic algorithms, and two examples which are genetic algorithms and simulated annealing. So to start off, exact versus non-exact strategies. So exact strategies, they achieve the optimal solution to a given problem, but they demand more computational resources and they demand more execution time, such as the brute force algorithm. But the non-exact strategies, they demand less computational resources, less execution time, but unfortunately, they do not guarantee the optimal result. But they explore the problem in an intelligent way and they find good results in a feasible time with fewer resources. An example of non-exact strategies are heuristics and meta-heuristics. So heuristics. Heuristics revolves around the idea of that it's a problem-based design. It's only tailored to a particular problem. A single heuristic can only solve one problem. So an example of a heuristic algorithm is nearest neighbor. So nearest neighbor is a greedy search algorithm where it searches for its nearest unvisited neighbor and goes to it. Then iterates by moving through the closest neighbor and the closest neighbor until it reaches all of the neighbors available. So the problem is that it's easy to implement, it executes quickly, but it can miss short routes due to its greedy nature. It's good for small instances, but it's poor for large instances. So that's why we move to meta-heuristic algorithms. Meta-heuristic algorithms are non-problem based design algorithms. They are generic and they can deal with different problems by just tuning its inputs. So an example of meta-heuristic algorithms are genetic algorithms. Genetic algorithms are basically just based on the idea of natural selection and genetics. So think of it as a parent and a child. So each individual represents a solution in a search space. So we start with a parent solution, and then we want to move from one solution to the other. So we want to move to the child solution. But how can we move from the parent to the child solution? We have three different operator types. So we have selection operator, which is basically that the child solution inherits all of the characteristics of the parent solution. Or we have the crossover operator, which is basically that the two operators, the two parent solutions, they mate in order to produce a child that's a mixture of both, a mixture of characteristics of parent 1 and parent 2. And finally, we have mutation, which is basically that the child inherits some random genes from the parent. A fitness score is given to each individual, which just shows the ability of an individual to compete. How good is this individual, which is the solution, compared to the others? Another meta-heuristic algorithm is simulated annealing. So simulated annealing starts with just two basic ideas, which is an initial solution and an initial temperature. The temperature controls how likely the algorithm is to accept worst solution it explores in the search space. So let us think of the temperature as a threshold or a margin that I cannot bypass or go under. So at first, we start with an initial solution and an initial temperature. Then at each step, a new solution is generated by making just a small change to the current solution. So if we have an objective function if we have a solution that's S, and then the new solution is S prime is evaluated based on the using the objective function, if S prime provides a better solution, then logically S prime is the new solution and S is just not our solution anymore. But what if S prime is worse than S, but I might still accept it? So what controls my acceptance is basically the temperature. The temperature controls whether I would accept S prime or not. So after each iteration, we have something called the cooling schedule, which is that the temperature is decreased according to a predefined cooling schedule, which determines how quickly the algorithm converges. So when we reach our lowest temperature, the algorithm is terminated, or when we reach a predetermined number of iterations, the algorithm is just terminated. So before moving into machine learning, let us cover the points we talked about. We talked about exact versus non-exact strategies, and we tackled two non-exact strategies, which were heuristic versus non-heuristic versus meta-heuristic algorithms. We tackled two meta-heuristic algorithms, which were genetic algorithms and simulated annealing, and we covered only one heuristic algorithm, which was the greedy nearest neighbor search. So now let us move on to machine learning, but bear in mind that all of the algorithms that we talked about before machine learning are just fixed algorithms. They do not learn any patterns, or they do not learn much about the data available. But now let's move to machine learning. So machine learning is just basically that the algorithm learns patterns from data to make predictions or decisions without hard coding all the rules. Just like the algorithms that we talked about in the heuristic and non-heuristic and meta-heuristic algorithms. So we have three types of machine learning we're going to tackle, which is supervised, unsupervised, and reinforcement learning. So in our case, supervised learning is that the model is going to learn from labeled history to predict ETAs, constraints, or good moves that the model can use in order to reach the optimal point. Then we can look into unsupervised learning too, where the model is going to be pre-trained on abundant, unlabeled routes in order to learn just a general representation. It will not learn the real traffic jams, the real construction issues such as supervised learning. But then comes the upgrade, which is reinforcement learning, where the model learns through an agent. The agent learns through rewards. So the agent is put into an environment, and then the agent learns from doing some actions and getting rewarded on these actions. So if the agent takes a decision and this decision results into a good positive result, then the agent is rewarded. If the agent takes a bad decision, then the agent is punished, and then the agent learns about the positive and negative actions that it took, and then this can drastically improve the results in our use case because it's all based on trial and error. So the machine learning use cases that we can talk about is that in our case, we're going to first train a baseline model. which will just learn about ETAs, service times, and demand models. So the constraints are just more accurate, and this shrinks our search space in order to decrease the time that the model would take in order to learn about things that you can already learn if we just feed it to the model. Then we can give our model a push by proposing a strong initial routes or fixed key variables that think about it as if we're fixing our main hyperparameters. And these hyperparameters, we already know that we would want to use them. So fix the key variables that you already know the model won't need to learn because it's already going to be fixed because it will just yield the best result. Then in a third part is that the model will start searching. So the model we can use, for example, transformers, so we can score insertions or moves and even learn by focusing on the best results and the worst results, such as when we talked about reinforcement learning. And we can even scale our model even more by learning from high quality solvers other than the model itself. And finally, we can just keep on the trial and error reward that would make the model even better and better and better by time. So the machine learning algorithms that we suggest for our use case is gradient boosting, graph neural networks, transformers, imitation learning, reinforcement learning, and hyperheuristics. So we talked about machine learning. It's the types that we can use, such as supervised learning, unsupervised learning, and reinforcement learning. But now we're going to dig deeper in reinforcement learning. So the main issue in network routing is that traditional routing method like a fixed map, it falls short in the dynamic environment of a city. It cannot learn the traffic jams. It's unable to learn the construction obstacles, and etc. So our main issue is that how can we solve this problem? So we can solve this problem by using a model that can learn through trial and error these obstacles, these daily life, these just daily life ideas. It can learn everything. So that's why we use reinforcement learning. So our main challenge is that just traditional routing follows a fixed map. It's fast, but it fails completely during a traffic jam. So reinforcement learning acts like a smart GPS. It learns from experience. It tries a route, sees a delay, and gets a penalty. It tries another route and gets through quickly and receives a reward. So this dynamic helps the model learn faster and more accurately than any other fixed algorithms. So let us take an example where the agent is a delivery driver and is taking a decision that he'll take a certain action, which is that he'll not take the highway, he'll take the main street instead. So the environment, the entire city with its real-time traffic, road closures, and weather are simulated. The reward is the feedback. Was that a good decision or a bad decision? So how will the model learn whether it was a good decision or a bad decision? The model is going to learn through the results. So if the results were fast delivery time, low fuel cost, and a happy customer, then the model will learn that this is a right action to take. But if the result was getting stuck in traffic and a late delivery, then the agent would be penalized and would learn that this action was bad action. So Let's take a quick look at reinforcement learning algorithms. So first, let us talk about Q-learning. So Q-learning is just the most basic reinforcement learning algorithm. It's like memorizing a cheat sheet of the best moves, which works for simple problems but fails for complex ones because the cheat sheet becomes too big. And it just doesn't make sense that I make my model memorize more than it can just generalize. Because at the end, my end goal for my model is to generalize. So we can then talk about DQN, which is instead of a cheat sheet, it uses a neural network, a brain, to guess the best move, allowing it to handle much larger and more complex problems. And then finally, and the most interesting one, which is the actor critic. So the actor critic is an advanced method that uses two brains working together. One to decide on an action, which is the actor, and another one to judge if this action was good or bad, which is the critic. This teamwork often makes it learn faster, make it more reliable, and even more interesting. So reinforcement learning is just the main reason for nearly all robots, and because reinforcement learning gives machines the ability to learn complex behaviors on their own, from teaching robots to walk on uneven grounds like here, to mastering strategic games such as chess, for example. So now let us move on to a demo that we can take a look at. So in this demo, we are going to test and compare the results between BFS, which is just a normal tree-based optimization algorithm, and a heuristic algorithm, which is the greedy nearest neighbor. So these are just my function definitions. Let us start from here. These are the number of points or nodes. We're just setting the seed to avoid randomization. And this is just my start index just at 0. So we're going to run the code, and we would want to see the results, and we would want to compare the results between the two algorithms that we have, as we said, the BFS and the greedy nearest neighbor. So let us start by just having 2 points. So the results are nearly the same because it's not a complicated problem. You just have 2 nodes and you want to reach from this node to this node in the shortest path. But let us now increase our points from 2 to 5. As we can see now, the greedy nearest neighbor has a longer path than the BFS. But the greedy nearest neighbor has a shorter runtime than BFS. So as we said, the nearest neighbor is fast, but it will not always reach to the optimal result. But BFS is considerably fast, but it's slower than greedy nearest neighbor, but it reaches the optimal result, or even let's call it a better result. So let us now increase the number of points to even 8. So as we can see, the BFS is also better at reaching the shortest path than the greedy nearest neighbor. So what we can learn from here is that when choosing an algorithm, you need to think of the trade-off you'd have between reaching the optimal goal or the shortest path and the lowest time. So you'd want to have this trade-off between having the fastest and at the same the most accurate with the most accurate algorithm. So thank you for watching this video, and I hope you have fun solving the hackathon.